As the sixth planet from the Sun, it stands out with its striking ring system, composed of countless rings and rock particles that range from minuscule grains to house-sized boulders. These rings, discovered by Galileo in 1610, have since been a subject of wonder and scientific inquiry. The planet's physical characteristics are as fascinating as its cultural impact. With a mean radius of 58,232 kilometers, Saturn is over 9 times wider than Earth. Despite its massive size, it has a surprisingly low density, so low that it would float if placed in a vast enough body of water. Saturn's atmosphere is mostly hydrogen and helium, creating a gaseous outer layer above a potential solid core. Its fast rotation leads to an oblate shape, bulging at the equator and flattened at the poles. This rapid spin also contributes to the planet's varied weather patterns, including powerful storms and winds that can reach up to 1,800 kilometers per hour. The planet's 62 confirmed moons, including Titan, the second largest moon in the solar system, add to its uniqueness. Titan, larger than the planet Mercury, possesses a thick atmosphere and even lakes of liquid methane and ethane, presenting a world of its own for exploration. The allure of Saturn extends beyond its physical attributes to the mysteries it holds. The planet's internal structure, the composition of its rings, and the potential for life on its moons are subjects of ongoing research. The Cassini spacecraft, which orbited Saturn for over 13 years, provided a wealth of data that scientists are still deciphering. The recent changes observed in Saturn's atmosphere and the dynamics of its rings challenge our understanding and invite further investigation. The Cassini spacecraft embarked on a historic odyssey to Saturn, becoming one of the most ambitious and successful missions in the exploration of our solar system. Launched in 1997, Cassini's journey culminated in a 13-year sojourn around Saturn, where it unveiled a trove of discoveries that have reshaped our understanding of the ringed planet. Cassini's revelations began with the intricate dance of Saturn's rings, which were found to be more active and dynamic than previously thought. These rings, a laboratory for planetary formation, displayed propeller-like formations and hinted at the possible birth of new moons. The mission also observed the Great Northern Storm of 2010 to 2011, providing insights into the atmospheric phenomena of gas giants. One of Cassini's most profound discoveries was the detection of active, icy plumes on the moon Enceladus. These plumes, ejecting water vapor and ice particles, suggested the presence of a subsurface ocean, raising the tantalizing possibility of habitable conditions. Similarly, Titan, Saturn's largest moon, was revealed to be an Earth-like world with methane rain, rivers, lakes, and seas, further fueling our curiosity about life beyond Earth. The mission's endgame, the grand finale, saw Cassini perform a series of ultra-close orbits, diving between Saturn and its rings. It was during these daring maneuvers that Cassini collected key data which provided a new temperature map of Saturn's atmosphere. This data suggested that auroras at the planet's poles, generated by electric currents from solar winds and charged particles from Saturn's moons, could explain the mysterious heat of Saturn's upper atmosphere. But Cassini's legacy extends beyond these discoveries. The spacecraft's measurements have led to a better understanding of the anomalies in Saturn's axial tilt and orbit. Recent research, incorporating Cassini's findings, suggests that the tilt of Saturn's rotation axis is due to the migration of its satellites, particularly Titan. This migration is causing Saturn to tilt more over time, with predictions that the inclination could be more than double in the next few billion years. Moreover, the mission has shed light on the possible origins of Saturn's tilt. A grazing encounter with a lost moon named Chrysalis may have contributed to Saturn's current obliquity and the formation of its rings. This encounter, occurring around 160 million years ago, could have removed Saturn from Neptune's gravitational influence, leaving it with its present-day tilt. Saturn's rings have been observed to be disappearing, stirring concern and curiosity among astronomers and space enthusiasts alike. These rings, composed of countless icy particles, range from minuscule grains to boulders as large as mountains, and have been a defining feature of Saturn since their discovery in 1610. However, recent observations, particularly from the James Webb Space Telescope, have highlighted changes within these celestial bands. The observations from Webb's Near-Infrared Camera (NIRCam) have shown that while Saturn appears dark due to methane absorption, the icy rings remain relatively bright. This contrast has allowed for a detailed examination of the rings and their structure, yet it is this very ice that seems to be depleting, leading to the rings' gradual disappearance. The potential causes behind this phenomenon are as intriguing as they are complex. One primary factor is ring rain, a process where electrostatic forces pull ring particles into Saturn's atmosphere, causing the rings to lose material at an alarming rate of approximately 44,000 pounds per second. This erosion is further exacerbated by Saturn's magnetic field, which creates electric currents within the rings. These currents induce magnetic drag, leading to a slow spiraling of particles toward the planet, where they eventually fall into the atmosphere or crash onto its surface. Another contributing factor could be the gravitational interactions between the rings and Saturn's moons. As these moons orbit, they tug on the rings, potentially leading to the dispersion of ring material. Additionally, collisions between ring particles can eject material out of the rings, further contributing to their diminishment. The implications of Saturn's ring disappearance are profound. The rings are not only a symbol of the planet's identity, but also a record of its history and a laboratory for studying planetary ring dynamics. Their loss would not only alter Saturn's appearance, but could also provide insights into the planet's evolution and the processes that shape our solar system. The disappearance of the rings also raises questions about their origin. If the rings are indeed vanishing, they may be a relatively recent addition to Saturn, possibly formed from the remnants of moons or comets that were torn apart by the planet's gravity. This suggests that the rings we see today could be just a transient phase in Saturn's long history. At Saturn's North Pole, a six-sided marvel known as the hexagonal storm commands attention. This atmospheric anomaly, larger than Earth itself, is a jet stream that encircles the pole. The hexagon's sides are approximately 15,000 kilometers long, which is more than the diameter of our planet. Although the Cassini-Huygens visited Saturn's hexagon in 2006, it was first visited during the Voyager mission in 1981. The hexagon's behavior is unusual for several reasons. Unlike other clouds in Saturn's atmosphere, it does not shift in longitude and maintains its position with a steadfastness that defies the dynamic nature of the planet's weather patterns. The hexagon rotates with a period of 10 hours, 39 minutes, 24 seconds, which intriguingly matches Saturn's radio emissions from its interior, suggesting a deep-seated connection to the planet's rotational dynamics. The scientific community has proposed multiple theories to explain the hexagon's formation. One hypothesis suggests that the hexagon forms where there is a steep, latitudinal gradient in the speed of the atmospheric winds in Saturn's atmosphere. Laboratory experiments simulating these conditions have produced similar regular shapes, with 6 sides being the most common, but the exact mechanism at play in Saturn's atmosphere remains elusive. Another theory posits that the hexagon is a result of fluid dynamics. It could be a standing wave pattern created by the planet's rapid rotation and the atmospheric winds that vary with latitude. This explanation aligns with observations of the hexagon's rotation rate and its persistence over time. Further complicating the enigma is the hexagon's color change. Within a span of 4 years, from 2012 to 2016, the color of the hexagon shifted from what looked like a bluish hue to a more golden hue, a transformation observed by the Cassini spacecraft. One explanation for this color change is the pole's exposure to sunlight caused the increased production of photochemical haze, which changed the color over time. Despite the wealth of data and the various theories proposed, there is no consensus on what causes the hexagon. Its existence challenges our understanding of atmospheric physics and planetary science. The hexagon serves as a case study of the inexplicable phenomena occurring on Saturn, representing the limits of our current scientific knowledge and the potential for future discoveries. The hexagon's enigmatic presence at Saturn's North Pole is a reminder of the complexity and wonder of the universe we inhabit. It stands as a testament to the enduring mysteries of the cosmos, inviting us to continue our quest for understanding through observation, experimentation, and exploration. As we peer into the depths of Saturn's atmosphere, the hexagon beckons, a puzzle waiting to be solved, a story waiting to be told. The hexagonal storm at Saturn's North Pole, with its perplexing stability and color changes, serves as a reminder that there are still many mysteries to solve. The lack of consensus on its origin underscores the need for continued observation and research. As we strive to understand these enigmatic features, we gain a deeper appreciation for the complexity of the forces that shape our universe. In contemplating the future of Saturn, we must also consider the eventual fate of our solar system. Current models predict that, in billions of years, the Sun will expand, potentially engulfing the inner planets, and then shed its outer layers, leaving behind a white dwarf. This transformation will undoubtedly have profound effects on the remaining planets, including Saturn. Whether its rings will still exist or its moons will have migrated to new orbits, Saturn's story will continue to evolve as part of the solar system's grand narrative. If you want to see more content like this, click on one of the cards